All right, so this new unit with magnetism, I'm going to start on the reference table and just show you the equations that we're going to be using. So we've got magnetic field strength. We'll talk about where these apply, just like when we had electrostatics. We talked about, some of these equations were single, for a single charge. Sometimes an equation was for two charges, next to each other. So I'll talk about these, but I'm just going to kind of highlight them. We have this magnetic force equation here. You might notice something different. You might not even notice it actually, but there's a symbol in there that none of the other equations that we've seen yet have in them. So when you look at any of the other problems, equations that have multiplication, they just put the two variables next to each other. But here we see like a regular old-fashioned X for multiplication. Any thoughts about that? Why that is? Yeah. Cross product. That's exactly right. So these little arrows on top of the variables are telling us that these are vectors. And then when you do operations with vectors, we have two different types of multiplication that we can do. We can have the dot product and the cross product. And we'll see both of those right here. So this equation is exactly the same as the equation right below it. But they're just doing the cross product for you. Okay, we'll talk more about it when we get there, but I'm just kind of like highlighting that those two equations are linked together. All right, and we see another cross product here, and right below it, they're doing the cross product for you. So we actually won't be doing the cross product in this class, but just for your future reference, you're going to see that in your upper level math classes, and then you'll know, oh, that applies to physics sometimes. All right, so we'll just do the absolute value stuff, and we'll end up taking a sine of an angle. All right, then, so these are both equations for the magnetic force. Okay, they apply to two different things. The first top one, this applies to a charged particle moving through a magnetic field. This one applies to a wire of length L in a magnetic field. So wires will feel forces in magnetic fields when currents is flowing through them, but also just individual charges will feel forces as well. Okay. There's some really similar stuff in these two equations. I hope you guys can kind of see that they're very much related, right? Current is how many charges are moving by per second. That's a rate thing. Velocity, is a rate. It's how far you go per second. So there's tons of similarity here. Actually, they're they're just different ways of writing the same equation. All right. We got the dot product that I kind of told you about. So here it is. And then they do the dot product for you. So these two equations go together. We'll be using the second one. Okay. This weird little symbol on the end, that represents magnetic flux. Okay. Magnetic flux. For the brief explanation that I'm going to tell you right now, it's basically how much of your magnetic field is passing through a certain given area. And we're going to see that with our coils of wire, how much magnetic field is inside that ring of wire. Okay. And now the last two, they're kind of independent of each other. Again, you might see that there's some connections here, but it's not like one is like a rewritten version of the other. And that's the electromotive force. So this is going to have to do with induction. Flux capacitor, Andrew. Yeah, this is what allows time travel to be possible. So we'll come to all these equations next class. But I just wanted to show you where they were and show you, what we're going to get to. So So far, what we talked about yesterday was that we know about magnets. A pretty traditional magnet that we've seen before is just a bar magnet. This has magnetic field lines around it, and magnetic field lines go from north to south and look something like this. Uh-oh. Did the call drop? Are you guys still there?
Yeah.
Yep.
Okay. It disappeared on my screen. All good. All right. So, and the significance of these field lines, these magnetic field lines, is that if you take another magnet, so I'm going to take just another smaller bar magnet, and you place it in this field, well, then you guys know opposites attract. So the north will point towards south.
Mr. Varney.
South. Yes.
So when you have like iron shavings or something that are magnetic, do those
Correct.
also have a north and a south pole?
Yes. So we're going to talk a little bit about this, but there is something called the atomic magnetic moment, and it has to do with the spin of the electrons. Okay, electrons, we know they spin. They have quote unquote spin. It's a characteristic of the electron. And when they're moving in their orbitals, they're moving in these certain patterns. And depending on how they're moving, the atom itself will have a magnetic moment, just like I told you a coil of wire will create a magnet. Well, the atom itself is basically gets its own little magnet, basically. And that magnet from the atom itself, there are these regions within certain materials, like you're saying iron filings. So I'm going to talk about iron specifically, where all the atoms in a certain region kind of line up with one another. And then if you're in a magnetic field, all those different regions line up with the magnetic field. And so that'll make it, it's the reason why magnets stick to steel, but they don't stick to other things like copper.
Gotcha.
Okay.
Thanks.
Yep. And so we'll see, steel, you can kind of, so those domains, they actually call them, not regions, but they call them domains. They're just like, kind of like almost like cells inside the metal. If you put it in a strong enough magnetic field, they'll all line up, and then you get rid of the magnetic field. They'll mostly stay in alignment for a little while. So you can actually charge it. If you've ever taken a magnet to I don't know if you guys have ever done this, but a screwdriver, you can take a magnet and actually rub it on the screwdriver. And if you just kind of continuously rub it on the screwdriver in the same direction every time, you're going to line up all those different domains. And then when you get rid of the magnet, that screwdriver will remain magnetic for a little while. And you could touch it to things. And then slowly over time, if you bang it on the table or if you heat it up, the molecules get vibrated out of alignment, and then it's no longer magnetic. I mean, it's no longer a magnet. It's still magnetic if you brought a magnet and touched it. Yep.
They have like screwdrivers with magnetic tip.
Yeah, so that's different. That's a permanent magnet that's like built into the screwdriver. I'm talking about if you just take any metal rod, you can magnetize it for short term, right? We can create a magnetic field that when we get rid of, I'm not talking about putting a coil around it. I'm not talking about like leaving it attached to the magnet. I'm saying actually you can just get all the domains to line up, get rid of your magnet, no current, no nothing, and it'll still hold that magnetism for a little while. All right. So we also talked about the fact that compasses have magnets. So the needle of a compass is actually just a magnet. And you usually see them like this, and the colored inside is north. And so here on Earth, we said, all right, cool. Magnets on Earth, when you have them, they point towards the North Pole. But if the North is pointing towards the North Pole of Earth, that means that inside of Earth, the magnetic south is at the north end. It's a weird thing to think about, but that's the way it works. Okay. So now we know how magnets behave towards each other. Opposites attract. If you take a north and a north, put it next to each other, they repel. A south and a south, they repel. You felt that all before. You've done that. You've had hands-on with that. The thing that we don't really have a lot of hands-on with is the fact that charges will feel a force from a magnet as well. Okay. And it's not going to be the same. It's actually kind of odd. It's not going to be the same like pulling towards a magnet. You can't take an electron next to a magnet and just expect the electron to move towards it. So here's my magnet, north, south, and let's create some field lines. And we're going to kind of look in this region. I'm going to do a zoomed in view of this in a little bit. But if I just take an electron and I place it here, everything we've seen before, like electron in an electric field, is just going to feel a force kind of parallel to those lines. That's not the case. And as a matter of fact, that electron by itself will feel no force at all if it's just sitting still. If it's just sitting there, it's not going to feel a force. In order for the electron to feel a force, it has to be moving. Okay? So now, if this electron is actually moving in the magnetic field, so it's flying in here, the velocity, I'm going to draw this picture, kind of get rid of my magnet. We're going to put, here's our magnetic field lines down, just making them all parallel and simplifying this a little bit. That's my magnetic field. And now if I have a velocity this way, this electron is going to feel a force pushing it into the page. Okay, so it would be, instead of like you wouldn't be able to see it from this view, it would travel this straight line from our view, but it would be moving farther and farther away from us into the page. So let's draw that exact picture from slightly different viewpoint. Same exact picture, but now I'm going to draw a top view. So I'm going to say side and top. So if I'm looking down from the top now, I'm looking at the back of all of my vectors, right? You remember I thought of the vectors as having a tail. And so looking at the back of them is always an X with a circle. And if my electron is traveling to the right, eventually it's going, when it gets into this field, it's going to feel a force upward and it's going to curve up. Not up, I guess, away from us, right? Hey, what's happening? Oh, nice. So does everybody get that this is the exact same thing from two different viewpoints? So how do we figure out which way that electron is going to move? We're going to use another right-hand rule. Yesterday, I showed you a right-hand rule. This is going to be a different one. There's two ways to do this. I'm going to draw my terrible hand for people who are at home and can't see me, but I'm going to actually think of it either just a flat hand, like you were waving to someone like a high five, or this is the way I was always, for people at home, I'm going to draw the picture, but I'm going to describe it right now. I'm like pointing with my thumb sticking up, but my other three fingers are at a 90-degree angle to my pointer. So let's see how this rule works. If I was talking about and it's my right hand. So actually, I want to make my thumb pointing straight up. So let's draw that. Mr. Davino just left. He would have liked to see my beautiful hand drawing. Hands are hard. All right, so we're gonna say V cross B. If you guys remember from peeking at this sheet, here it is, V cross B. So V is the first thing we're gonna do. We're gonna keep our fingers pointed in the direction of velocity. Okay. Our palm is going to be in the direction of B. So in this picture, I can't even see my palm. I'm gonna draw a dotted B. If I was turning my hand over, same hand, you'd see the palm of my hand, and now you'd be able to see the B itself. Okay, so V, B. And your thumb, I put my V in the wrong spot, sorry. V is always your fingers, and your thumb is your force. Let's try that the other way, that I was just thumb, pointer, and then my art skills are really here's the top of my thumb sticking straight up, and my fingers. Can you guys, people at home, you're probably struggling with what I'm drawing here. All I did is rotate the hands in this bottom picture. V, and the three other fingers are my B, but thumb is always the force.
It looks like a duck.
Yeah, I know.
But it makes sense.
Okay. Actually, I should just like Google the right hand rule. Just show you. You actually, if you could see my video camera, can you guys see my video camera?
Yeah.
There you go. This is what I'm
Don't
doing
shoot.
in my hand. Okay. Or you can just say V pointer finger, B palm forces your thumb. Oof. So when I do that here, V is my pointer, B is my palm. If I was to take my hand, here's my right hand, my fingers are in direction of V. To get it to be pointed down, I'd have to rotate my hands. And actually, you won't see anything because this is the side of my hand that has my pinky on it. And that means that V is this way. Here's the palm of my hand pointed down. So that's B. And my thumb would be sticking into the paper. This top one is like, I'm holding my right hand there, but I'd actually have to start rotating it until it's flat with the page. This hand is not using the right hand rule yet. From the top, might be a little bit easier to see. V, B, and the B is pointed down away. We wouldn't be able to see it. So our force is up. And in this picture, my force is into the page. Okay. Questions, comments, thoughts on that? So that's one of the right-hand rules. The other right-hand rule that we talked about yesterday is telling us how a moving charge makes its own magnetic field. So right now, this right-hand rule is the force that a moving charge would feel from a magnetic field. But moving charges create magnetic fields as well. So if we had a wire, and here's my wire. Let's go a little bit. And if its current is moving to the right, then we can use the right-hand rule to grab onto that wire and wrap our fingers around it. So here's my hand grabbing on. And this rule is a lot easier to draw. Our thumb in this case goes in the direction of I, and our fingers tell us the direction of B. So on the top, our fingers are behind the wire and pointing out towards us. And if I wrap all the way around the wire, my hands are kind of wrapping all the way around and they point into the page underneath that wire. And if we were going to kind of draw a side view of that, basically what we have is I'm behind the wire, and over here I'm coming in front and behind, and this would be sticking out of the page. It's almost hard to draw out of the page here. There's out of the page. This would be into the page. And since it's circular, we have in the back, we're sticking up, and in the front, our magnetic field is pointed down. So most of the time, it's going to be really helpful to do like a side view. This first one, what we call orthographic. Straight from the side, because basically all that geometry gets reduced into 2 dimensions. But you do need to realize that there is a round circular magnetic field around this. And that would be, the farther away you get, that magnetic field is going to get weaker and weaker, but it's still there. Nice, all these concentric rings around the wire. So far, so good. Questions or comments about that? So now, if we take that wire and we wrap it into a loop. So here it is from above. And if we say, all right, let's put a current in this, then we get our right-hand rule. If I grabbed onto that, what would it look like? My hand would be thumb pointing that way, fingers wrapping around. And that means on the outside, my fingers are all pointed down. But on the inside, my fingers are pointed up. And my hands could slide all the way around this, and everywhere on the inside, that magnetic field would be pointed up. And that means we've created an electromagnet. Because all of those upward facing magnetic fields in the middle add up together. And this, if I turn it slightly on its side, here's my coil. And if we do lots of them, right, we could see this as like a lot of coils of wire. We end up with, let's make sure our current's going in the right direction. This is I. Means we have I this way here in the front. We would get a magnetic field in the middle pointed up. So this would be the north of the electromagnet that we just made. If we put the current the same direction in this one, where we're coming in from the back, and that's actually this way. In from the front, in. Every one of those would have its own magnet, and they'd all add up, and we'd end up with electromagnet inside of that coil. Questions, comments, thoughts? So if you, so easy, we all got it, no problem. Let's think about one. Here's our wire. I put a current in here. Let's say it's going this way. Take a second and draw the magnetic field above and below this wire. Right hand rule. Draw the wire, pretend like you grabbed onto it. So I grab onto this with my right hand. Hopefully everybody sees that on the top. Oh my gosh, I drew a left hand. Can you believe that? What was I doing?
I was about to say the hand looks kind of weird.
It's a left hand. That's not what your right hand looks like.
It's perfect for Kyle.
Is he lefty? All right, so
Yeah.
my fingers.
Yeah.
All right. So this is the back of my hand, and we can't see all the fingers wrapping around. So into the page on top.
Wait, Mr. Varney, I'm not sure if this is a silly question, but like, how do you know which way like the thumb should be, like on the bottom of the wire and the top of the wire? As long as
It
like, the
doesn't
thumb's
matter.
pointing in the direction.
It's a good question. I'll do my best to draw a right hand that has the thumb on top.
Is it just like
If
a
this
matter
was
of
my-
clockwise or counterclockwise that we're worried about?
Correct.
Okay.
So both hands have my fingers wrapping around in the, I don't know, it's weird because it's not really clockwise or counterclockwise, but in this direction. Does that make sense? Both pictures have the fingers
Yeah.
wrapping around like that arrow is. Okay. And so now we have our magnetic field around our wire. It's going to get weaker as we get farther away. But what happens if I say, hey, there's an electron moving this way. Let's call it electron with a velocity. Now we have to do V cross B, the funny other right-hand rule. V on your fingertips, B on your palm or your other 3 fingers if you make that right angle. So don't forget, just because I drew those dots there, it still has a magnetic field out here. It's just weaker, but it's still pointed straight out towards us. So if you took a right hand now out here and this would be, trying to draw this so that you could tell it's like the palm of someone's hand. How's that for a palm? Can you tell that that's the palm of someone's hand? Is that weird? Does that make it worse? V and B, your palm is facing up because the magnetic field is facing up. And which way is the force? Down. So this thing, the electron, will feel a downward acceleration. Questions, comments, thoughts about that? Okay.
Should it be like out of the page, like
What out of the page?
before?
Which way is the thumb pointing?
Like that?
Your palm should be pointed towards the this is the magnetic field. It sticks off your hand. So when I put this on the paper, I'm gonna stand up here. V and B should be this way, sticking straight out of the screen. So my thumb is pointed towards the floor.
Oh, yeah.
You got it? Okay.
Wait, Mr.
Now-
Barney, I got lost.
Go ahead.
I was following before. I thought we were following the position of the hand on the wire for like the palm being the field and the thumb being the force.
Yes, that is.
So how come, so like on the wire, you have the thumb like pointing with the wire, but then when you drew the thumb again below it,
Oh,
it's
two
pointing down.
different right hand rules. So there's the right hand rule is applied differently in those two situations.
Okay,
So,
can you say again why the bottom one then is facing that way?
okay, I'm gonna try and describe this, and you can try and literally take your right hand and then make your fingers point towards V. So now they're pointed across your paper to the right. And you can rotate your hand 360 degrees. You could have your palm straight down towards your paper or your iPad screen or whatever, or you could rotate it and you could have, if your iPad screen, is sitting flat on the desk, let's all pretend that, sitting right on the desk. So we could rotate our hand, and if the iPad is sitting right on your desk, those dots are telling me the magnetic field is pointed towards the ceiling. And so I would have to rotate my hand, keep it pointed so my fingers are in the direction of V. I'm going to rotate it until my palm faces the ceiling as well. And that's what I tried to draw in this picture over here on the side.
So in the picture, is that palm, like I guess, is the thumb pointed down or out of the page?
Down.
Okay. Because the
The thumb
magnetic
is
field
the-
is pointing, the magnetic field's pointing out of the page.
Correct.
Okay, that makes sense. Thanks.
Yeah, that's, I'll even put like that. I don't know if that helps or not, but yeah.
Mhm.
Okay. Last thing I want to say, I know you guys all want to run, and you can run if you need to, but what if I said, hey, this electron is stuck in a wire? Well, that blue electron in this wire if it was traveling this way, that would mean we have a current to the left, right? Conventional current goes the opposite direction of electrons. And so when you have two wires next to each other, they actually feel a force that repels them, a magnetic force repelling them. And that's going to be an equal and opposite force. And that comes from the fact that they're pushing on all those moving charges that are in the wire. And I think that's a good place to stop. All right. Thanks, guys.